Hello everyone, welcome to Autodesk Advanced Manufacturing Summit for the year of 2020. First of all, I would like to say thanks for all the participants attending this presentation. Let me introduce myself first. My name is Rajesh Khanna, working as a technical sales specialist with Autodesk India in Digital Manufacturing Group. Having more than 2 decades of manufacturing work experience, joined in Delcam in 2011. I am driving business in Indian subcontinent through partner collaboration to generate revenue in the areas of subtractive manufacturing and drive the customers to the future of making things. So, in the today's topic, when to use 3+2 and 5-axis milling techniques. We will cover on the advantages over each other, and we will see on dynamic machine control where the programmer can completely change the 3-axis toolpath into a 3+2 axis toolpath, and we cover on automatic collision avoidance, which will automatically create a 5-axis toolpath from a 3-axis toolpath, and we will see the better techniques comparison between the 3+2 and 5-axis continuous, and we will also cover on 5-axis limitations and its solutions. Let's start with 3+2 machining. It is a technique where we lock 2 of the rotational axes in a 5-axis machine and execute 3-axis milling program with the cutting tool. Hence the name is called 3+2 machining or a positional 5-axis machining. Let us see how to create a 3+2 toolpath creation in PowerMill. It's an aerospace component where we need to create a roughing toolpath over this particular pocket, which is also available in 3 different planes. So for that, I will start with creating a work plane. For that, I select the bottom surface and selecting my center of selection option. So this is my output work plane. And I also need to create a local work plane to create a 3+2 toolpath. So for that, I'm selecting my align to geometry option and placing my cursor over the surface. You can see that Z-axis is perpendicularly sits over the surface. So I'm activate that particular work plane. Then I'm creating a block here. For that, I'm selecting the bottom surface and side surface for the height. So you can able to see that block is created locally. I already predefined all my cutting data and my movements within a template. So I'm calling that template here. I had input all the parameters and readily available for calculating the toolpath. So I calculated this toolpath first with all the values. It is created here. So now I need to do the array over the rest of the planes. So for that, I'm selecting my output work plane and right click over my pre-created toolpath. So for that, you can select transform option and then you can select rotate, select number of copies and have 2 copies here, and it is located in 120-degree angle. You can able to find that it is having a preview. If everything is fine, just accept it. Now you can able to see another 2 toolpaths are created in 2 different planes. Let us join all the 3 toolpaths in a single NC program. For that, I'm just right click over the NC program and say create NC program here. In this one, I'm selecting post processor. Here I'm using a HAS UMC 750 and my output work plane is 1. So I'm selecting that. Then I'm combining all the toolpaths here within a single NC program and apply accept it. So now you can able to see that all the 3 toolpaths has been combined in as a single NC. You can also see the simulation of this particular NC program by right click over the NC program, say simulate from start and play the simulation. You can able to see that it starts from the first pocket and automatically it turns its plane to the other pockets and completing all the 3 pockets with the roughing program. So like that, we can able to create a 3+2 toolpath creation. You can also able to see a machine simulation here. So you can right click from the NC programs, say simulate from start, you can play, and there you can find whether you have any collisions takes place between the machine parts to machine parts, or maybe a holder to the machine parts. So this will verify the entire toolpath, which is free from gouge and collision. We had seen how to create 3+2 programming. Now take a look how it is getting performed in the machine tool. So for that, I'm selecting my machine tool position form, make my all axis home position and make it 0 there. Now you can able to see that machine axis limits in Z, X and Y, and B axis is -35 and +110, and C axis is all the way 360 degree. So let me start simulating this toolpath. Once you're done, you can able to see that C axis is moved to 180 degree and B axis is performing 90 degree here. Let me start playing the simulation. You can able to see that 2 of the rotary axis is getting fixed or locked, and a 3-axis machining is getting performed. Once it is completed with the depth, you can able to see that one of the axis is getting rotated. Here it is going to C axis 300 and it is making a 3-axis a local roughing toolpath. Similarly, it will rotate to the other movements and it will complete all the 3 profiles here. So this is a perfect example of a 3+2 machining, or we can simply call it as positional milling. Let's move to the dynamic machine control option. This option will interactively helps the user to convert the 3-axis toolpath into a 3+2 machining axis toolpath. The main advantages of using this type of machining is where we can utilize minimum overhang and with shorter holder, which leads to faster feed rates. This will reduce the cycle time too. Let's simplify the process of creating 3+2 axis toolpath from a 3-axis toolpath using dynamic machine control option. This enables you to quickly and easily improve the machine tool access to the workpiece with the same holder profile and the overhang of the cutting tool. For this, I'm having an example of a mold part. Also, I'm using a Rai machine tool for my simulation. Also, I had pre-created a 3-axis toolpath using a 12 mm ball nose cutter. Let me open the settings of the toolpath here. If you look at the tool axis page, I had set the tool axis as vertical, so it is a pure 3-axis toolpath. Let me start simulate of the toolpath from the beginning. So it starts the toolpath from the top. After moving it some level, so a collision is detecting between the model and the holder. So the simulation has been stopped. Take a look at the area of colliding. So now without changing the holder profile or overhang of the cutting tool, we can go and tilt the tool axis with the help of dynamic machine control option. For that, I'm going to right click over the tool, select the dynamic machine control option. Here you can directly grab the handles of the tool axis, and also you can select the point of the cutting tool and you can move the various regions and ensure whether any other collision is taking place or not. So if everything is fine, you can update the toolpath here and accept it. Let me start the simulation again. You can able to see that the tool axis stick to the user defined position and it is completely avoiding all the collisions between the holder and the model here. Let me stop the simulation. If you go and look into the settings of the toolpath again, where your tool axis change to fixed direction and it grabs some vector values from the user defined settings. Let me switch on my machine tool form, play the toolpath again here and play it. Now you can able to see that A and B rotary axis stick or locked to a certain position and a local 3-axis is performing now. So by using this dynamic machine control option, we can create a 3+2 toolpath for deeper mold, or maybe it is inaccessible in a 3-axis areas. Let us have some advantages of 3+2 machining. The main advantage to adding a 3+2 setup to your current vertical machine is that it allows a workpiece to be machined from all sides. This reduces the need for additional setups, thereby lowering the cycle time and reducing costs. The 3+2 also use a shorter or more rigid cutting tool than a 3-axis machining, resulting in greater dimensional stability, increased tool life, reduced cycle time, and better surface finish. Let's move to 5-axis machining. 5-axis continuous machining, or also called as 5-axis simultaneous machining, involves using a CNC machine to move a part or cutting tool along 5 different axes simultaneously. This enables the machining of very complex parts, unlike 3+2 operations where the part is in a fixed orientation. We had seen what is 3+2 axis machining and what is 5-axis machining. Let us apply both in this particular component and see how and where to apply it. Before that, let us analyze what is the drafts available in this particular example. For that, I'm going to switch to draft angle shading mode, and you can able to find the red color highlighted areas are undercut. So it is not possible to do it in a 3-axis machining. So we have to adopt either 3+2 axis machining or a 5-axis continuous machining. In this case, for roughing, I will take 3+2 axis machining, and for finishing, I am using a 5-axis continuous machining. The reason why I am taking a 5-axis continuous for finishing, this can be eliminate blend lines between the two toolpath segments. First, we will start with 3-axis machining. So I already pre-created that. From the top view, you can able to find the maximum amount of removed with the 3-axis machining. Now we use the 3+2 techniques and remove the undercut regions. For that, I already pre-created a work plane for the first position, so which is in this corner, and also I will go and see the draft analysis again. Now this is okay with the 3-axis positional milling, but here you can see that still it is undercut with this work plane. It is fine. I'm going to apply this 3+2 machining over this area first, and we can find that undercut regions were removed by the 3+2 machining. And for the next position, I'm using another work plane which is in this corner. Let me analyze the draft angle again. Now here it is fine. So I have already created a second positional toolpath to remove the material at this corner. Now the entire material removed within the particular pocket. Let us go for finishing strategy. Before that, I had created a swap finishing and applied over the surfaces of the either end of the part, so for the better understanding. Let me simulate this first. You can able to find here the complete flute is touching the surface. This will give you a better finishing with a single cut. So the similar kind of approach, we are going to do it in the pocket region also. So let me start from the first one. This is not a correct toolpath, but I will show you what is happened inside. If you look at the settings here, I use a swap finishing with flat end on planes enabled. And if you look at the toolpath also, it's fine. And if you see the simulation of this toolpath, it starts fine. And when it comes to some point, the holder is colliding with the model. So without changing the holder and the overhang, we have to correct it. Let me go to the second solution here. If you go into the settings, in this time, I use follow surface laterals. So the tool will follow the laterals of the surfaces. Let us see the simulation of this toolpath. You can able to find it crossed this end, but here it is getting colliding. Let us take the correct toolpath. If you go and see the settings here, where I used minimum fanning distance to avoid the collisions and maximum tilting angle. So here I had not used the follow surface laterals. Let me simulate this toolpath. I had not changed any profile of the holder or overhang of the tool. If you see the simulation of this one, it is perfectly okay with the entire pocket. So this is a simple technique how to create a swap finishing within the closed encounters. Finally, we will move to the bottom region. Here I am used a continuous 5-axis machining also. I use the tool axis settings as from curve option to avoid the collision completely. You can able to find under tool axis. I used from curve. I already pre-created here, which is available at the top of the part, which is the counter of the top profile. Let us see the simulation of this one. You can able to find that it is continuously do the finishing operation, stop for a while, take the machine tool form, play again. You can see that there is a continuous motion in the rotary of A and E axis. So now with this, we can able to understand how and where to apply 3+2 axis and a 5-axis toolpath strategies. We had seen how to convert a 3-axis toolpath into a 3+2 axis toolpath by using a dynamic machine control option. But here we are going to see how to convert a 3-axis toolpath into a 5-axis continuous toolpath when there is a collision taking place between tool assembly and the model. By using this function, we can use shorter holders and minimum overhang for better finishing and dimension accuracy. Let us see how this automatic collision avoidance works with this mold tool example here. For this, I'm using a Huron KX200 as my machine tool file for the simulation purpose. Also, I had pre-created a flow line finishing toolpath strategy to cut the part at the bottom of this fillet radius. Let me open the settings first. In this toolpath form, I'm using tool axis as vertical, so it is a simple 3-axis toolpath. Under the same tab, you can able to find automatic collision avoidance option. For this toolpath, I had disabled it and I calculated that. Let me simulate the toolpath first. Now you can able to find the PowerMill is giving warning where a collision is taking place between the model and the holder. So the simulation has been stopped. Take a close look where the collision is taking place. So now come to the second toolpath. Go to the settings. With the same toolpath with the same parameters, I had enabled my automatic collision avoidance option on. Then if you come under the collision avoidance page, you can able to find different tilt methods. For this toolpath, I'm using automatic as my tilt method, and also I had given some tool clearances and holder clearances here. Also, I had provided some smoothing distance also. With this, I'm going to simulate the toolpath here. Let me open my machine tool position form. Now you can able to find the 3-axis toolpath is converted into a 5-axis toolpath to avoid those collisions. So by using this automatic collision avoidance, the user can automatically tilt its tool axis to avoid collisions taking place between the holder and the model. So why we need a 5-axis machining? For this, we will take an example of a ball nose cutter which are used extensively for finishing operation of 3-dimensional models. So it is not recommended to use this tool perpendicular to a surface. It is because of several problems with the usage of ball nose while machining. The first one, by its form, the absolute center of its tool does not have any cutting edge, which means there is no cutting action. In addition, the chip evacuation at the central section is very difficult since the body is practically zero. The second disadvantage is in using this tool in a perpendicular to a surface, that most of the 4 flutes tool have only 2 flutes at the edge of the central portion. The final one, the use of perpendicular to a surface decreases considerably their duration of tool life. So it is necessary to tilt its tool axis to avoid machining perpendicular to a surface. So for better understanding of 5-axis simultaneous toolpath, let us have a closer looks between 3 types of toolpath. Here I had pre-created a 3-axis toolpath, 3 plus 2 axis and a 5-axis continuous toolpath. Let's start with 3-axis toolpath. Let me select a segment at the center and right click over that and say simulate from here. If you play the simulation from that point, most of the time the tool contacts the workpiece at the bottom of the tool, which is not recommended. Let me stop the simulation to the 3 plus 2 axis toolpath. Start the simulation from the same point. When it comes to 3 plus 2, though the bottom of the tool is not as a contact point, the tool cuts at a specific location rather than utilizing the entire sphere portion. This will create a tool wear at the particular region only. Let me start the simulation again and I will move to the 5-axis toolpath here. Coming to the 5-axis toolpath, let me start from the simulation from the same point. If you look at from the side view of this, here the tool contacts the workpiece at the side edges. This obviously produces good cutting action with the uniform wear over the entire side edges. So this gives better understanding of 5-axis simultaneous comparing to rest of the toolpaths. If you look at the advantages of 5-axis continuous machining, mainly it will eliminate blend lines between individual parts, efficient machining on complex and feature-rich parts, reduced programming time compared to 3 plus 2 programming, better surface finish and mainly used for reduced number of setups. Let us compare the limitations with examples over 3 plus 2 and 5-axis continuous machining. In general, 3 plus 2 roughing have more advantages compared to 5-axis continuous roughing, but there are some exceptions like in impeller machining. In PowerMill, we have dedicated blisk roughing and finishing toolpath strategies to complete the part in most efficient way. With the use of ball-nosed cutter, we can able to complete roughing in a single toolpath strategies rather than using a 3 plus 2 machining where the toolpath have to create serious number of work planes with different angles. This obviously need a programming skill. So as you can see that a roughing toolpath has been created with a 5-axis motion using the dedicated blisk roughing toolpath strategy. Let me stop the simulation here. Also you can see finishing toolpath strategies. With a single one we can complete the hub finishing at the bottom, as well as we can complete in a single toolpath strategies for the blade. Let us see how to create a 3 plus 2 axis machining with the same part. For that I will move to the position of the here. As I said earlier, we have to create multiple number of segments of toolpaths over the particular region. So the first one I'm going to start with here. Let me start with creating a work plane at point. So for that we have an option at PowerMill to create a work plane to the view axis. So if you click that, you can see that Z axis created perpendicular to the view. So accept it and activate that one. So now we have to create a boundary over this region and we will start creating the toolpath. So here I'm using a user-defined boundary. With the sketch option, I quickly draw my boundary over this particular region. Accept it and I will create a roughing toolpath strategy here. For that I'm creating a model area clearance. From this one I'm creating the work plane first. So I already selected. So the block, I have to use a global transform. So I had created the block in this form. It is a pre-machined turned component. Then we come to the tool part. I'm selecting a 10 bull nose here. Then I will produce some cutting data also. Let me start calculate the tool path for this position first. You can see that this particular area has been completed. So similarly, you have to create another tool path and work plane for different regions here. This really a time consuming process and obviously need programming skills. For that, we have a continuous 5-axis toolpath strategy, which is called Blisk area clearance, where the toolpath can be generated as a continuous motion, which obviously requires less skill in the programming side, and as well as a single toolpath, it will be run very smoothly. At the same time, we can also create finishing toolpath strategies with a continuous motion. This will eliminate the blind lines between the segments where it happened in a 3+2 machining. Take another example of engine wall port machining, where 5-axis continuous roughing also takes more advantages over a 3+2 roughing toolpath. Autodesk PowerMill have dedicated port machining strategy to reduce programming time, as well as it outputs safer toolpath with reduced cycle time. This kind of port machining mainly used in high performance engine to reduce the friction. To create a port machining toolpath, the programmer have to simply specify the pattern at the center of the port, and he can select the dedicated roughing toolpath strategy. If you look at the settings of this particular toolpath, the user have to specify the tool, and in the port area clearance have to specify the pattern, and the tool axis sets to automatic. So he can able to produce a single tool path for roughing for the same operation. If you go for a 3+2 machining, the programmer have to create multiple work planes and multiple tool paths to complete the same profile. If you look at the simulation of this tool path, it starts safely from the start. Then it is completely avoiding all the collisions between the holder and the model. In the similar fashion, it is also have a dedicated finishing toolpath strategies for finishing as a spiral motion or as a plunge motion. By using this dedicated strategy, 5-axis continuous roughing take more advantages over 3+2 roughing. Let us have some examples where 5-axis continuous toolpath works more efficiently over a 3+2 machining. In this particular example, the toolpath was generated over an undercut region, which is not possible in a 3-axis machining from the current setup. So there are two options, either have to go for a 5-axis simultaneous or a 3+2 machining. For the most efficient way of machining, here we use a taper tool where the sides of the tool touching the wall, so we can go larger depth of cut by using the 5-axis continuous option. So it is efficiently tilts its tool axis at the corner radius and with the adjacent surfaces of the part. At the same time, if you use a 3+2 machining here, the tool edge only will contact with the part, so we have to reduce the depth of cut, which is obviously increase the cycle time, as well as there will not be any smooth transition takes place at the corner radius of the part. In the second example here, we are using a chip radius cutter with this single blade part machining, where the flat bottomed tool machines very efficiently by maintaining a controlled lead angle. Here 5-axis continuous tool path takes more advantage over a 3+2 machining for finishing operation. If we use a 3+2 machining, we have multiple segments of tool paths, which creates line marks at the joining of each tool path. At the same time, for doing roughing operation, 3+2 is the best method. Let us discuss 3 different ways of machining using a 5-axis machine tool. So the first one is 3+2 axis machining. Here you can expect predictable results as there is no simultaneous rotary axis movements. In this technique, we locked both the rotary axis and cut the part using 3 linear axes only. But it will be increase your programming time as you need to create multiple work lanes and multiple toolpaths from different angles if the part is feature rich. As we are creating multiple segments, you can also find some blend marks between individual toolpaths. So the next one, we move to 4-axis machining. Here, by locking one of the rotary axis, mostly we do it for C-axis, which will increase surface finish as there is no axial reversal, or you can say singularity, so there is no rapid accelerations. But at the same time, it is not suitable for more complex and feature-rich geometry. And the final one is a 5-axis continuous machining. We are utilizing both the rotary axis to make 5-axis simultaneous movements. Because of this, there will not be any blend marks found, so there is no requirement of polishing. By using all the 5-axis movements, we can cut feature-rich parts with shortest possible tool overhang. So, based on these 3 different techniques, we can choose the best way of machining as mentioned here. Another commonly found limitation issues in the 5-axis are the minimum linear limits in the either X or Y axis. So here we are using a DMU50 machine. With the settings, we can find that the X-axis limits, Y-axis limits sets within the machine tool. Here in the X-axis sets to -250 to +250. The Y in -245 and positive is 80 mm, and Z-axis similarly you can see for the B and C axis. So here I have a part. I need to perform a deburring toolpath over the top of these 2 surfaces. For this, I have already pre-created a toolpath here where my settings sets to machine tool axis control as free. So with this, I'm going to see the simulation first. Before that, I will show you the manual movements in the X and Y axis, whether it can be performed or not. So in the Y axis, you can able to see that it hits the maximum limit before reaching end of the part, but in the minus side, it is fine. At the same time, if you look at the X axis side, you can see that either end is fine to cut. Let me simulate this toolpath first. You can able to see that it starts from back end of the Y axis, so there is no limit issues, and even in the X axis also. When it reaches to the maximum limit of 80 mm, the PowerMill is giving the warning here and the simulation has been stopped. So to overcome this particular issues, we can able to use the polar machining option, and we can do the machining completely with the help of rotary axis movement. Let me open the second toolpath here. In this case, my machine axis control changed to polar. I'll also using the Y axis is my lock position. Also, I enabled use complementary angle option. So with that, I'm going to see the simulation. You can able to find that it utilizing the rotary axis of C, and you can able to complete the profile without hitting any limits. Here we had locked the Y axis, so it moves the X maximum and it is completing the profile. Let me open the settings again, copy the toolpath. This time in the machine axis control, I'm using the X axis lock position and calculate the toolpath again. And if you see the simulation now, you can able to see that it moves to the back end of the Y axis and it is completing the part without hitting any limitations. So by using the polar machining option with the complementary angle, you can able to perform the machining without hitting any limitations by using the rotary axis positions. So the next limitations found in the 5-axis machines are machine singularities. Because of this, we will find rapid accelerations in the rotary axis movement. This mainly occurs when the tool axis is close to the machine singularities. Look at the video in the left. Is the toolpath motion look smooth? Obviously, the answer is yes, because there is no machine tool file attached to it. So there is no machine limits and configuration sets with the machine tool movements. Let's look at the second video in the right, and we can able to observe there are two rapid accelerations found in the C-axis because here we attach the machine tool for the simulation. This is because of sudden changes in the model profile from positive to negative drags, which is also close to singularities of the machine. These movements can be closely observed using simulation analysis available in the PowerMill. Look at the part using draft analysis shading. We can able to find the sudden changes in the highlighted area from negative to positive draft. When the machine singularity is closer to this machine axis moment, we can able to find rapid accelerations in the rotary axis of C. Let us solve the singularity issues in two different methods. In the first method, we place the part over an angular fixture to move the tool axis away from the singularity. Now, from the video in the right, you can able to find the machine tool runs smoothly without having any rapid accelerations in the C-axis motion. This solution can be derived with the same machine tool and the same toolpath strategy without changing any of the parameter. And also we have second solution here by adding more points in the point distribution settings, which is available in all PowerMill toolpath strategies. We can reduce the impact when simultaneous 5-axis machining close to the machine tool singularity. By reducing the value of point separation angle, we can get the better results. Though this solution is not more efficient compared to the part mount over an angular fixture, but it is cheaper and easier method of reducing the negative effects of this problem. So here we have the results by using different values in the point separation angle in the decreasing order of value. For this, we utilize Huron KX 200 5-axis continuous CNC machine, which is a head-head configuration. This is the sample part, which is in the top left, and we start from point separation angle disabled, and you can find the dwell mark, and it is reduced using with the value of 0.5 and further get reduced using 0.25 to avoid the dwell mark. Thus, we solved the issue. Finally, let us discuss about the advantages and disadvantages for both 3+2 and 5-axis continuous machining. As I said earlier in the presentation, in 3+2 machining, we can use shorter and rigid cutting tools, which enables faster feed rates. This leads reduced cycle time, high dimensional accuracy, as well as reduced number of setups. The tool moving distance is shorter, so the programming code is lesser. Coming to the disadvantages, user have to create multiple work planes and tool paths in different tilted position to cover the entire workpiece. Sometimes this will take more programming time as well as need of skillful programmer. Blend line will appear between individual toolpath segments, thus need manual polishing. Coming to 5-axis continuous, in the advantages side, no special fixturing is needed compared to 3-axis machining, reduced number of setups, so we can reduce the cycle time as well. We can eliminate blend lines between individual toolpaths, so no polishing required. It also reduces special cutting tools and costs. Effective length of cutting edge leads to better surface finish and to get better tool life. So the only disadvantages compared to 3+2 machining is the machine axis rigidity is comparatively lesser. So in general, for finishing operation with more complex shapes, 5-axis machining is better. And if you come to 3+2 axis, which allows the cutting tool angle towards the workpiece, so it is mainly suitable for positioning the part for faster feed rates and speeds. mainly used in the roughing operation. So with that, I'm ending my presentation. Thank you all.